Good evening, faculty and students of George Mason. This is David Hayes speaking, and me, along with my team team members for our 151 mechanical engineering class, Jackson Noose, Kyle Ross, and Thomas Chapman. We will be discussing one of the 14 grand challenges that the National Academy of Engineering put forth to all entrepreneurs, students, and aspiring engineers in the world to tackle in order to keep everybody alive in the world. That challenge was getting energy through fusion. The embodiment of the NAE's goals can be expressed in this quote: continuation of life on the planet, making our world more sustainable, secure, healthy, and joyful. Kevin Warner and Glenn Jones, in their 2017 article for the journal Energies, review the 2015 conference for the United Nations and how they decided that replacing all energy production to renewable energy by 2028 would successfully reduce the global temperature to 2 degrees by that time and would help sustain the Earth and everything that lives on it. They argue, however, that these goals were inaccurate and they didn't account for the increasing population and the also increasing energy demand that would result. This can be seen in the graph for the global model for energy production to 2100, where the green area would be the amount of energy demanded that would have to be switched to renewable from the black area, which was the non-renewable energies. Nowadays, nuclear fission is the only way we're getting energy from nuclear means, and that is because that is the only technologies available for us to efficiently get that energy. Fortunately, here on the right, you can see on the top right the tokamak built by ITER, which is a collaboration of many countries: the United States, Korea, China, Japan, the European Union, and Russia. And on the bottom right here is our group's rendition of that through.
Many countries around the world are working to find solutions to our problem, and many countries are working to find solutions differently. However, many of them are included in the ITER and the NIF, and they're all working to find different solutions to our grand challenge. Now, within these solutions, nuclear and mechanical engineers must work hand in hand together to provide the solution. Now, while nuclear engineers are the main proponents of this technology, mechanical engineers are still required, and they have a large impact on the development of further technology due to the nature of this field. Mechanical engineers are required in the production of the fusion reactor, something nuclear engineers cannot do on their own. A background of nuclear engineering may be helpful, however, to manufacture the design of a nuclear reactor, a mechanical engineer is required. Now, nuclear engineers deal with the theory of fusion and not the execution of it. So, in the ITER, mechanical engineers are just as necessary as the nuclear engineers. To turn fusion energy into physical reality, mechanical engineers are required to design restraints, shielding, and improve safety measures on the physical design of the reactor. One such example of this is the tokamak blanket, withstanding a maximum thermal load of 736 megawatts at its first layer, according to ITER. Now, nuclear engineers can calculate the heat that will be created, but to manufacture and design the blanket, a mechanical engineer is required. Mechanical engineering plays a major role in the success of fusion energy. Aside from manufacturing and designing of the parts of the tokamak, there is a need for understanding of the theory of fusion. Being an integral part of making a tokamak work, nuclear engineers use the theory of their knowledge to influence the design of the tokamak. As previously stated, though, the mechanical engineer now must work with the client, which is the nuclear engineer. And the nuclear engineer and the mechanical engineer work side by side in designing the tokamak. And this is important to create a successful reactor. Only with the applied knowledge of both the mechanical and nuclear engineer will the tokamak reactor be successfully manufactured and operated. Now, while both of these engineers are required to accessing the fusion energy, sometimes more research and development and sometimes funding is required from outside parties. And this is something that the ITER has very many problems finding.
The most pressing issue that needs to be developed by research is heating a plasma to a sufficient yet sustainable reaction temperature while keeping the plasma stable during the process. We have had many test runs in which the desired temperature was reached, but they could only sustain it for a short period. On the other hand, we have been able to sustain a stable plasma for the needed amount of time, but at a lower temperature. It's the issue of achieving both criteria simultaneously that requires intensive research. There was minimal university research done on this topic because of the extreme cost of the experiments. A few examples of these projects include the East Reactor in China, the Wendelstein 7X in Germany, and ITER in France. Research is typically done on a larger scale by cooperating countries and top-level scientists. That's not to say universities cannot help with smaller areas of research. So far, we have developed 2 devices that use magnetic fields to contain the plasma and keep it stable. These are the tokamak and the stellarator. The stellarator is more stable but harder to build and is behind on research development. The tokamak, on the other hand, is easier to build, but the ease has a cost in stability. The Princeton Plasma Physics Lab is doing work trying to improve the stellarator to make it more feasible. Another example is the University of Rochester using its renowned Laboratory for Laser Energetics, the LLE. They have become a front-runner in research on a type of fusion called direct drive laser fusion, which uses lasers to input the necessary energy for fusion.
Many different companies and countries focus on the development of fusion technology to this day. Each one has differing agendas, and while monetization and development of this technology for a commercial basis is the main goal for the vast majority of these syndicates, others have different end goals. Many different organizations and foreign government branches are either directly focusing efforts on, or diverting a large amount of resources to, the development of fusion technology. One of the largest of these is the U.S. Department of Energy's FES, or Fusion Energy Sciences program. The FES program focuses on the National Academy of Engineering's Grand Challenge related to fusion power, and works directly for solutions to the challenge's remaining obstacles. For example, as stated on the FES program's website at energy.gov, in March of 2020, the FES program announced a $3 million funding plan for research on measurement and monitoring of hot plasmas, a goal that, if completed, could provide even simpler solutions for sustaining the superheated plasma found inside of the experimental fusion reactors the FES program works with. While this research is extremely important to the future of a fusion program, many other funding plans exist on a range of disciplines contained under fusion research. The FES program's approach to fusion energy is directly tied to the theoretical nature of a sustainable fusion reactor. Unlike entrepreneurs and companies currently researching the topic, the FES program doesn't aim to monetize the technology directly, and instead simply wishes to understand the science behind fusion itself. This type of research is arguably more important than simply building a reactor and testing it, as without the knowledge to bring these plants to life sustainably, there's little to no point. While no mention of employment opportunities is available on the FES program's website, employment in the U.S. Department of Energy would most likely be the first step in working on the project, as the FES program is a branch of that department. Employment opportunities for the Department of Energy can be found on their website, also at energy.gov. Now, as you can see, an extremely large amount of time, effort, and resources has gone into development on fusion technology, and the NAE's Fusion Challenge specifically, from the companies attempting to commercialize the tech to national governments and other organizations simply seeking to understand quantum mechanics further. Nuclear fusion is a large part of many people's lives and has the potential to revolutionize our modern world even further.